It's my pleasure to introduce Daniele Semola. He's going to speak about Ricci Curvature, fundamental groups, and the Milnor conjecture.
Thank you very much for the introduction, and thank you very much to all the organizers for inviting me. It is really a great pleasure to have the opportunity to present this talk. And as the title says, I'm going to be talking about the conjecture of Milnor, and let me start by reminding you of what the conjecture said. So in 1968, John Milnor conjectured that if you were given any smooth, complete n-dimensional Riemannian manifold with non-negative Ricci curvature, then its fundamental group should be finitely generated. And the aim of this talk is going to be to make a brief overview around this, about the developments in the last 50 years around this conjecture, with a particular focus on a family of counterexamples that we recently built in joint work with Elia Bruè and Aaron Naber. And more precisely, what we did in this joint work was given any subgroup of the rationals modulo the integers, then what we do is that we build a smooth, complete 7-dimensional Riemannian manifold with non-negative Ricci curvature, so it fits into the realm of the Milnor conjecture, and it has the property that the fundamental group is isomorphic to the given subgroup of the rationals modulo the integers you were starting with. A couple of comments about this. So first, we are actually building a family of counterexamples, so not just a counterexample. And the second, maybe trivial comment is that in this family of examples, actually there really are examples with infinitely generated fundamental groups. In particular, you can find the group Q mod Z itself, which is of course not finitely generated. And here is a brief, very rough outline of my talk. So there will be some background relating concerning relationship between lower bounds in the Ricci curvature and control on the fundamental groups in the setting of smooth Riemannian manifolds. I will discuss a series of positive results around the Milnor conjecture that have been obtained by several authors in the last 40, 50 years. And in the second part of the talk, I would like to discuss the construction of the counterexamples, and there will be two parts. One, the very first part will be dedicated to the construction, to a kind of topological outline for the construction of the counterexamples. And in the second part, I would like to discuss more in detail a few of the more geometric steps in the construction, where we try to endow actually this topological differentiable manifold with a metric of non-negative Ricci curvature. In the end, if there is still time, I would like to mention a couple of maybe obvious open questions related to this subject. And of course, feel free to interrupt me at any time if you have questions, comments, remarks. So let me start with something very basic. One of the most fundamental tools in the study of Ricci curvature lower bounds, and in particular in the study of non-negative manifolds with non-negative Ricci curvature, is the so-called Bishop-Gromov volume monotonicity, which, let me remind you, says that the scale invariant volume ratio in manifolds with smooth, complete Riemannian manifolds with non-negative Ricci curvature is non-increasing. And in the very same paper where he raised the conjecture that we stated in the previous slide, Milnor, building on top of the earlier version of the Bishop-Gromov monotonicity originally due to Bishop, proved that in the setting we care about, so in the setting of smooth, complete Riemannian manifolds n-dimensional with non-negative Ricci curvature, if you stare at any finitely generated subgroup of the fundamental group, then this finitely generated subgroup must have polynomial growth with the growth order less or equal than the ambient dimension. Let me draw a couple of elementary conclusions from Milnor's polynomial growth theorem. So first conclusion is that a couple of explicit examples of possible fundamental groups are actually already ruled out by Milnor's polynomial growth theorem, and in particular, the free group with two generators is ruled out by Milnor's theorem. For the very simple reason that it has exponential growth, it doesn't have polynomial growth, and moreover, also the cyclic group, the group Z to the n plus 1, and actually you can raise it to any power strictly larger than the dimension. This group has polynomial growth, but the growth order is larger than the dimension, and so it is still ruled out by Milnor's theorem. So once we have Milnor's polynomial growth theorem, one can appeal to an abstract and celebrated theorem of Gromov, proved in 1981, to the effect that if you're given an abstract finally generated group, and you assume that it has polynomial growth, then it must be virtually nilpotent. Where, let me recall that virtually nilpotent means that this group must have a finite index subgroup which is nilpotent. And I think it was Gromov itself to ask the question of whether in this geometric case of fundamental groups dealing not with general abstract groups, but with fundamental groups of manifold nonnegative Ricci curvature, his theorem could be made effective, where by effective, I mean, we mean that the constant, the index of this nilpotent subgroup should be bounded by constant only dependent on the dimension. And this stimulated a lot of work. Let me just mention here, let me be very brief here and mention the work of Fukaya Yamaguchi in '92, who devised a new proof for the virtual nilpotency of fundamental groups in the setting of manifolds with non-negative and almost non-negative sectional curvature. And later, the argument was pushed forward by Kapovic, Petroni, and Tushman, who were actually able to really prove Gromov's claim in the setting of sectional curvature lower bound. And in the setting we care about, the setting of Ricci curvature lower bounds, we have the following theorem due to Kapovic and Wilking in 2011, which says the following. So usual setting, we are staring at a smooth, complete Riemannian manifold with a negative Ricci curvature. Then you can find the dimensional constant, a constant depending on the dimension, such that for any such manifold, if you stare at the fundamental group, then you can find a nilpotent subgroup of this fundamental group. Let me denote it by capital N with the following properties. The first property is that actually, as in Gromov's conjecture, the index of the subgroup is uniformly bounded by a constant only depending on a dimension. And moreover, the nilpotent group N has the following two properties. First property is that if you look at any finally generated subgroup of this group capital N, then you have a uniform upper bound on the number of generators that you need to generate those finally generated subgroups. And moreover, you also have a uniform upper bound only depending on the dimension. Actually, the nilpotency length turns out to be bounded by the dimension of the manifold. Let me draw a couple of more conclusions. So we see that we can rule out several more possible fundamental groups for manifolds with a negative Ricci curvature. If we now take into account also the dimensional bound. And in particular, we can stare at the group Z over 2Z raised to the power capital N and see that thanks to Kapovic and Wilkins' theorem, this cannot be the fundamental group of a manifold of an n-dimensional Riemannian manifold with a negative Ricci curvature as soon as the exponent of the group is sufficiently large. And at this stage, one might wonder whether one might ask the question of how far Kapovic and Wilkins' theorem goes from giving a full characterization of possible fundamental groups of Riemannian manifolds with non-negative Ricci curvature. And it turns out that if Milnor conjecture was true, then their theorem would have given basically a full characterization of possible fundamental groups of manifolds with non-negative Ricci curvature. And this is due to the following result of Wilking, who, building on earlier work due to Wei in 1988, proved that if you're given any, abstractly, any finally generated virtually nilpotent group gamma, then Wilking was able to build a smooth, complete Riemannian manifold with a negative Ricci curvature with fundamental group isomorphic to the given group gamma you were starting with. And let me, just for the sake of illustration, make the comment that, for instance, while previously we were ruling out abstract groups as possible fundamental groups of manifold with non-negative Ricci curvature, Wilkins' theorem, but actually this really goes back to Wei's work, tells us that we can find a smooth, complete Riemannian manifold with non-negative Ricci curvature such that its fundamental group is given by the so-called discrete Heisenberg group, which, if you're not familiar with, is just given by, you can think about it as given by the upper triangular matrix, 3 by 3 upper triangular matrices with the ones on the diagonal and integer numbers over the upper diagonal part. Are there any questions or comments on this? Okay, if not, the last abstract result about connections between lower bounds on the Ricci curvature and fundamental groups that I would like to mention is, has been known in the literature as Wilkins reduction. We might rephrase it, roughly speaking, by saying that roughly speaking, what Wilkins' theorem tells is that if a Milnor counterexample exists, actually there must exist a Milnor counterexample with abelian fundamental group. And more precisely, in the very same paper we discussed before, we can prove that if you're given any smooth complete Riemannian manifold with non-negative Ricci, then what's true is that the fundamental group is finitely generated if and only if any abelian subgroup of the fundamental group is finitely generated. And to end this first introductory part, let me make the comment that let me make a consistency check actually, and point out that in the family of our counterexamples, actually all the assumptions, all the conditions that are prescribed by the positive results that are discussed in the last few slides actually are met, of course, and in particular, Q mod Z is abelian, so all of its subgroups are, of course, abelian, and moreover, it fits into the realm prescribed by Kapovich and Wicky's theorem. In particular, each of its finitely generated subgroup is actually cyclic, so it has just one, it can be generated by just one element. That's it about the abstract results relating lower bounds on the Ricci curvature with the structure of fundamental groups. And the next thing, my next goal would be to review some of the earlier positive results about the Milnor conjecture. Let me start by addressing the case where one strengthens the assumption on the lower curvature bound from non-negative Ricci curvature to non-negative sectional curvature, which is, of course, a stronger assumption. In this case, a theorem of Gromov, going back to 1978, tells us that not only we have finite generation for the fundamental group, but we also have a dimensional bound for the number of generators, which is explicit. It is really free to the dimension of the manifold in the setting of smooth complete Riemannian manifolds with non-negative sectional curvature. Let me make the kind of historical comment that actually finite generation was already known since the work of Shiger and Gromov on the Soul theorem, at the very least. Let me also make the comment that actually in dimension 2, so in low dimension, the statement was known since much before due to work of Kohn-Bosseng in 35, and in particular in dimension 2, actually in dimension 2, a much stronger rigidity holds to the effect that a smooth complete Riemannian manifold, Riemannian surface with the non-negative Gaussian curvature, it must be diffeomorphic to a two-plane, or it is a silinear, it splits. Very well. So in view of the study in the case where we make the stronger assumption of non-negative sectional curvature, the first non-trivial case in the setting of Milnor's conjecture is the three-dimensional case, where there is a distinction between the assumption that Ricci is non-negative and sectional is non-negative, but still, even in dimension 3, the statement turns out to be true. So Milnor conjecture is true, and still, even in dimension 3, we have a much stronger rigidity going on. This is due to the following theorem of Gang-Liu in 2013, who proved that if we are given any smooth, complete, three-dimensional Riemannian manifold with non-negative Ricci curvature, then one of the following two possibilities must occur. Either the manifold is diffeomorphic to R3, so a very strong rigidity is going on, or it has a cover which splits the line isometrically, in which case we have a kind of dimension reduction because the split factor must have non-negative Gaussian. In particular, we go back into the setting of the previous theorems dealing with non-negative sectional curvature. Let me draw the obvious conclusion that, in particular, Milnor's conjecture is true in dimension 3. And let me also make the historical remark that the case of Ricci curvature positive, where by positive I don't mean bounded from below by positive constant, but that just positive everywhere, was considered with similar techniques based on minimal surfaces by Shen and Yao back in 1982. And let me also point out that the different argument to prove not the full diffeomorphic characterization of open free manifolds with non-negative Ricci, but just the statement of the Milnor conjecture in dimension 3 was found more recently by Pan in 2020. The next kind of the positive developments that I would like to review are those related to the volume assumptions on the volume growth of the manifold with non-negative Ricci we are studying at. Let me remind that by Bishop-Gromov volume monotonicity that we discussed in the very first slide, a manifold with an n-dimensional manifold with a negative Ricci curvature must have as at most Euclidean volume growth. So the volume of balls grows as most with the speed r to the n, where n is the ambient dimension. And in the case where the maximal possible volume growth rate is saturated, so in the case of Euclidean volume growth, Peter Lee and later Anderson with a different proof that actually not only the fundamental group is finely generated, but it is really finite under this assumption. And on the other extremum of the possible scales of volume growth, let me recall that Calabi and independently Yao proved that a complete smooth Riemannian manifold with a negative Ricci curvature, which is non-compact, must have a volume of balls which grows at least linearly. So we have an upper bound on the possible volume growth, which is given by Bishop-Gromov monotonicity, and we have a lower bound, a linear lower bound on the possible volume growth, which is given by this theorem of Calabi and Yao independently. And on this extremum, on the possible scales of volume growth, Sormani in 2000 proved that the manifold for which the lower bound on the volume growth is saturated, so under the assumption that they have linear volume growth, the minimal possible volume growth, the fundamental group is finally generated. And the model which that one should keep in mind for this lower bottom for the scale of rigidity is, of course, the model of the flat side index. Very well. The next kind of developments, positive developments around Milnor's conjecture, are those that I would like to review, are those related to the so-called asymptotic geometry of the manifolds and of their possibly of their universal covers. So maybe probably most of you are familiar with it, but let me introduce some terminology to deal with these notions, and in particular, let me introduce the terminology of let me define what it means in this setting to consider a blow-down or an asymptotic cone. So let me recall that in the set, the non-negative Ricci curvature condition is a scale invariant one, and the Gromov's precompactness theorem is in force under this assumption. So we can take pointed Gromov-Hausdorff limits, and we say that a Gromov-Hausdorff limit, a pointed Gromov-Hausdorff limit of a sequence of rescalings of the manifold with non-negative Ricci curvature we are staring at is called an asymptotic cone or a blowdown of the manifold. A couple of remarks about this notion. So in very strong contrast with the case of non-negative sectional curvature, where we have conicality, really conicality and uniqueness of asymptotic cones, this is not anymore the case in the case where we make the weaker assumption that the Ricci curvature is non-negative. And this is key for at least morally for the developments that we are going to discuss later. So two remarks. The asymptotic cone of a manifold with negative Ricci curvature doesn't need to be unique in this setting, nor it does need to be a metric cone. And these are two observations due to Perelman and Shiger and Kolding in the late 90s. Let me end this part by pointing out that several results about finite generation or fundamental groups of manifold with a negative Ricci curvature have been obtained by Sormani, building on earlier work by Abresch-Gromol, and more recently by Pan, under assumptions on the asymptotic cones, on the structure, and on the uniqueness of the asymptotic cones of either the manifold, the smooth Riemannian manifold we are staring at, or of its universal cover. Very well. Are there any questions or comments on this part? Okay. If not, my next goal is to start discussing and illustrating the structure of the counterexamples that we build in the joint work with Elia and Naber. So first, let me address a very basic and preliminary question, which is the question of the existence of manifolds with the infinite generated fundamental groups. And to the best of my knowledge, the first, the classical, and the first, I think historically, the first example of a manifold with infinite generated fundamental group is the so-called dyadic solid complement. This is usually the construction goes back to Steenrod back in 1943. And Steenrod, most precisely, proved constructed an example of a free manifold with fundamental group isomorphic to the dyadic rationals. Okay, word of history on it is that Steenrod actually credits Vietoris for the idea. And if you're not familiar with the construction of the dyadic solid complement, maybe you might be more familiar with the construction of the so-called Whitehead manifold, which has many similarities with the construction of the dyadic solid complement. Let me recall that the Whitehead manifold was the first example of a contractible free manifold, open contractible free manifold, not homomorphic to R3. Very well, and let me also point out that actually before Gang's view work in 2023, the work that I mentioned before, giving the full diffeomorphic characterization of open free manifolds with non-negative Ricci, open complete smooth free manifolds with non-negative Ricci curvature. So the question of whether the Dianic solenoid complement, so the three-dimensional guy built by Steenrod back in 1943, might be a potential Milnor counterexample was open, and this was explicitly mentioned in a nice survey paper by Sheng and Solmani in 2006. And to end addressing this question about the general existence of manifolds with infinite generated fundamental groups, if we completely forget about the requirement on the Ricci curvature lower bound, let me also mention a result which I'm not sure who to attribute to the effect that actually more in general, any countable group is the fundamental group of a F manifold. Very well. So before entering into the details of the construction of the family of Milnor's counterexamples, let me make a very rough comment about their structure. And the comment is that the structure, the very rough structure that you should keep in mind while we go through the details of the construction of the counterexamples is that of a fractal snowflake. And this self-similar and fractal structure is required in order to make compatible the following two requirements. So first, we would like the fundamental groups of the manifolds to be infinitely generated because we want to build counterexamples to the Milnor conjecture. However, we have a strong regularity condition, which is the condition coming from Kapovich and Wicki's theorem, which we might rephrase by saying that the local fundamental group, so the fundamental group generated by loops or by isometries that displace less than a given threshold, should be not only finitely generated, this is trivial, but should be locally uniformly finitely generated, which amounts to say that there should be a uniform dimensional bound on the number of generators for this kind of finitely generated subgroups of the full fundamental group. Very well, let me start addressing now the details of the construction of the Milnor counterexamples. So what we are going to do is we are not going to build the manifolds with the actual manifolds with infinitely generated fundamental groups. What we are going to do is we are going to build the universal covers. They are going to be pointed manifolds. They are going to be complete, smooth. They are going to have non-negative Ricci curvature, and they are going to be endowed with the free isometric action of the group gamma that we want to be the fundamental group in the end by isometries. Of course, the two perspectives are they are of course equivalent. The construction is going to be inductive, and let me set up the stage for the construction. So we start from any whatever subgroup of the rationals modulo the integer, and moreover we are going to fix a sequence of scales. They're going to be scales going to plus infinity, which are going to be scales that are going to play a relevant role for the geometric construction, and moreover we make the technical requirement that these scales are going to need to go to plus infinity very fast. Then at the level of the group, what we prescribe is that we would like to view the group, the infinitely generated group. We are going to assume, of course, in order to build actually counterexample to Milnor's conjecture, that the group is not a finitely generated group, but it's an infinitely generated group, subgroup of Q mod Z, and we are going to make the construction that we would like to view this group as a nested union of finitely generated subgroups that are going to denote by capital gamma I, and we make the assumptions that all the capital gamma I are going to be finite, and under this assumption you can easily check that all these groups are actually cyclic. In particular, we can denote by little gamma I the generator of the group capital gamma I, and it is elementary to check that for any such natural number I, you can find an integer such that the new generator, little gamma I raised to the power little kappa I, gives you the generator that you were staring at the previous step of the inductive construction. Okay, very well. So the next step, in order for constructing, in order to construct the counterexamples, at least in order to describe the topological structure, is that we are going to be a tree as a first very rough approximation of the universal cover together with its isometric group action. And the construction of the tree goes as follows. So in order to build a tree, you should imagine that you're given a family of half lines, and they are parameterized by the group. And in order to build the tree, starting from this family of half lines, what we are going to do is that we are going to make collapse sum of the parts of these half lines. And the formal way to do this is by defining an equivalence relationship. So more precisely, what we do is we stare at the product gamma cross 0 plus infinity, which denotes the half line I was mentioning a second ago. And we define the equivalence relationship, which says that little gamma little t is equivalent to little gamma prime little t prime, provided gamma to the -1 gamma prime belongs to the group capital gamma I, and the two time or spatial components say they are equal to each other and they are larger or equal than the scale where, let's say, the new subgroup appears. Let me make the obvious observation that the action of the group gamma by multiplication on the product gamma cross 0 plus infinity by multiplication on the first factor trivially induces an action of the group gamma on the quotient, which we would like to view as our tree approximating the universal cover together with the free gamma action for the Milnor counterexample. There are going to be a couple of very bad pictures in the presentation. This is the first one. This is meant to illustrate the structure, the rough structure of the tree that we build in order to approximate the universal cover. So let me make the comment that in this picture, the tree ends at the bottom of the slide, and it goes up forever on the top of the slide. So at each layer of the tree, we have that the vertices are indexed by a quotient of gamma modulo one of the subgroups of the finite subgroups that we defined when we set up the stage for the inductive construction. And in this picture, the choices that I made were that little kappa j is equal to 4 for this bottom layer, and little kappa j plus 1 is equal to 3 for the upper layer. Very well. Are there any questions or comments on this? Okay, if not, our next goal is to pass from the tree that we build as a rough approximation of our Milnor of the universal cover of our Milnor counterexample to an actual, at least topological, in the end, smooth manifold. What we're going to do in order to pass from the tree to a manifold is that we are going to replace each vertex of the tree with a copy of the free sphere across the 4 disk. And moreover, as we want to build a manifold without boundary in the end, the next thing that we are going to do is to associate to each edge in the tree a gluing along boundaries components, and this gluing along boundary components is gonna go as follows. What we are going to do is that for each new copy of the free sphere across the 4 disk, we are going to remove smaller copies of the free sphere across the 4 disk, and we are going to glue in one of the boundary components of the old guys, which is going to be given by a product of two free spheres, and we are going to be gluing this boundary component with the boundary component that we created by cutting a hole into one of the new guys with the gluing diffeomorphism. And one of my next goals is going to be to specify how this gluing diffeomorphism is chosen. And let me be precise and tell you explicitly that this gluing diffeomorphism needs to map a boundary component into another boundary component, and all the boundary components that are going on in this game are going to be diffeomorphic to a product of 2 free spheres. So here is another picture, which is meant to illustrate one of the gluing steps. So here I would like to illustrate one of the gluing steps in the case where the parameter for the construction is chosen to be equal to 4. So on the top, you should have in mind, the picture you should have in mind is that we are picturing one of the new copies corresponding to each of the vertices of free sphere across the 4 disk. And in order for the gluing to happen, to go on, what we would like to do is, as I was saying, is to cut 4 copies corresponding to the choice kj equal to 4 copies of the 4 disk from the larger blue 4 disk. And these are going to go together with the attached copy of the free sphere. And on the bottom, you should imagine that you have the manifolds constructed at the earlier stages of the inductive construction that I'm going to denote by m tilde j minus 1. They are not going to be diffeomorphic to an abstract copy of the free sphere across the 4 disk, but they are going to have ends which are diffeomorphic to annuli into a copy of the free sphere across the 4 disk. And in particular, they're going to have boundaries diffeomorphic to S3 cross S3. And the next thing that I would like to address is how to glue these boundary components into the new boundary components that we create when we cut the holes into the new copy of S3 cross D4. And this is what I'm going to do next. So what I'm going to do is to specify the choice of the gluing diffeomorphism in this construction. Let me point out that the choice of the glue diffeomorphism is important in order to specify the topology and the diffeomorphic structure of the N manifold that we are going to build. But in order to describe to illustrate the non-triviality of the choice of the gluing diffeomorphism, I need to tell you some preliminaries about the choice of the actions that we are gonna endow these manifolds with, because in the end, what is going to happen is that the choice of these actions, the non-triviality of these actions, is what is going to prescribe us the non-triviality of the gluing diffeomorphism while we go through the inductive construction. So let me make some preliminary comments about the structure of the actions we are going to endow the manifold with. So let me make the maybe obvious remark that the free sphere is endowed with a free circle action, which is the action inducing the so-called op vibration. And in particular, if you stare at the product of two free spheres, you have a free two torus action. You trivially get a free two torus action where one of the circles acts by op rotation on one of the two S3 factors, and the other circle acts by op rotation on the other guy. And out of this, you can get plenty of circle action by considering the embeddings of the circle into the two torus, which is acting on the product of two free spheres. And in particular, for any choice of a pair of integers, A and B in Z cross Z, we're going to denote by AB of action, the induced X1 action on the product of two free spheres through the embedding of the circle into the two torus, where we rotate at speed A on the first factor and at speed B on the second factor. Let me make the also elementary remark that if the pair of integers were chosen to be coprime, then the AB of rotational action that you get is going to be a free action. This is, of course, very relevant because we want to build fundamental group action in the end. So given these preliminaries on the action, I can now describe you how we want the action to act, let's say, on the manifold that we were building inductively. So as I was saying, the construction is an inductive construction. So you should imagine that at the early and inductive steps of the construction, the actions of all the generators little gamma 1 to little gamma j minus 1 have been defined on the earlier steps of the inductive construction. So up to the ends of the manifolds that are denoted by m tilde little j minus 1. And what we need to do in order to go on with the inductive construction is to describe the action of the new generator that appears at the scale little rj on the new portion of the manifold that you are gluing it while we go up along the tree. And what we stipulated is the action of the new generators little gamma j on the new copies of S3 cross D4 is going to work as follows. So we would like the new generator to act by op rotation with angle 2 pi over the product of all the kappa i's from I equal to 1 to I equal to j. And let me make the comment that this is actually the order of the new generator little gamma j. So we would like the guy to rotate with this speed on the S3, with this angle on the S3 factor, but we would like it to rotate with a different angle for this component. So we would like it to rotate with along the op vibration with angle 2 pi over kj. And if you unwind the definition, you can easily realize that this discrete action is going to be a sub-action of the continuous action.
Sorry, quick. So can I interrupt for a second?
Sure.
Can you remind what kj is?
So kj is the integer such that little gamma j to the kj is equal to little gamma j minus 1. Okay. Any other questions or comment? Okay. If not. So as I was saying, the action is going to rotate with angle 2 pi over the order of the guy on the free sphere component, and it's going to rotate with a much larger angle 2 pi over kj on the D4 factor. if you unwind the definition, as I was saying, then you easily check that this is going to be a subaction, a discrete subaction of the action that in the previous slide I denoted by 1, comma k1 dot kj minus 1, continuous S1 action. And now here is where the non-triviality comes from. In order for the construction, inductive construction to go through, we need to make a consistency check, because as the construction is inductive, we have that the action of little gamma j minus 1 has already been defined on the earlier steps of the inductive construction. And we also have a relationship. They are not independent, the two generators. And the relationship tells us that little gamma j to the power gamma kappa j is equal to little gamma j minus 1, whose action has already been defined. And in particular, if you go back to what I was saying a second ago, you easily realize that the action on the new copies of free sphere cross 4 disk, the action of little gamma j to the power kj, which is nothing but little gamma j to the little gamma j minus 1, is going to be by pure rotation on the S3 factor, because taking the kj power is going to kill the rotational component of the d4 factor. So the action of this guy is going to be by pure rotation on the S3 factor. But if you go back to the earlier steps of the inductive construction, the action, so the construction is inductive, so you're doing the very same at all the steps of the inductive construction, and you easily realize that the action of the same guy on the ends of the glued-in copies of the manifolds with the earlier steps of inductive construction should be actually a different action. So it should be a subaction, a discrete subaction of the action of the S1 action that are denoted by 1, comma k1 dot kj minus 2 of function in the previous slide. And if you unwind the definition again, then what you soon realize is that here is where the non-triviality of the gluing diffeomorphism comes from. And in particular, in order for this construction to make sense, you need gluing diffeomorphism phi j in the notation of one of the previous slides, which are conjugating the two actions. So they are conjugate the action rotating on both components with an action which is just rotating on one of the two S3 factors.
Sorry, can I ask a question again? So you want a diffeomorphism which is kind of like on H3 is upper triangular with ones on the diagonal, but with some number in the corner? Is that?
I'm not sure I got what you mean.
I mean, you have a diffeomorphism from S3 cross S3 to S3 cross S3, right?
Yeah.
I mean, it acts on H3, which is...
Yeah. Oh, yeah, sure.
And the
That's
matrix...
correct. That's correct. Now I see what you meant. That's correct.
The matrix is like a square, is like upper triangular with ones on the... So
I think that's right.
The diagonal and just one, this number, but whatever it is.
Yeah,
K1,
I think that's right. I think you're right. Thanks for the comment. Any other comment?
One question about the action on the D4 factor, because if how are you extending from S3 to D4? Because if it's just by
sure. Let me address this. Thanks for the question. I was really sloppy on that. So the action is going to be extended radially. So we are viewing actually once you define the action as S3, you can view the 4 disk as the word product of the interval with the S3, and we are gonna extend the action by a radial extension. Say.
Okay, but
okay,
you would still have like a fixed point somewhere.
Yeah,
no?
but where the fixed the fixed point on the D4 is going to be compensated by the fact that the action is free on the other component.
Okay. Yeah. Okay. Thanks.
So this makes sense if you want to. It really makes sense at the level of fundamental. So you can really build a free action because the non-freeness on the 4 disk component is compensated by the freeness on the free sphere component.
Yes. Thanks.
Okay, you're welcome. So the next, so that's the end of the very brief discussion about the very brief outline of about the topological, the diffeomorphic construction of the universal cover together with the free action of the fundamental group. My next goal is to address the geometry, the construction, the steps where we try to endow this smooth 7 manifold with smooth Riemannian metric with non-negative Ricci curvature, which must be, of course, invariant with respect to the action of the group gamma that we discussed that we prescribed in the previous steps of the construction. And let me make a couple of very broad comments about the geometry of these guys that we're going to build. So first comments I would like to make about the volume growth of these examples and their asymptotic geometry. So first comment relating to the volume growth. So if you go back to the discussion around the positive results about Milnor's conjecture, we realized that Milnor conjecture was known to be true under the assumption that the volume growth was maximal or minimal. And of course, we are very far away from these ranges. And in particular, the volume growth of the counterexamples and the volume growth of the universal covers actually too is going to be oscillating between rate r to the power 4. Remember that the dimension of the counterexamples is 7, so we are far away from the maximal volume growth, and linear, so it's going to oscillate back and forth between linear growth and growth at rate r to the 4. And second comment about the asymptotic geometry of the examples. So the other takeaway from the earlier part of the talk was that Milnor conjecture was known to be true under strong assumptions about uniqueness and conicality about the blowdowns of the manifold or its universal cover. And what happens in this family of counterexamples is that the asymptotic cones are really highly non-unique. And in particular, if you stare at the universal cover, you get a full family of asymptotic cones. They are all cones, actually, but they are cones over free spheres, and the radius of you get a whole family of cones, and in the family you get all the cones over the free sphere, where the radius of the free sphere goes from 1, the maximal one, for which you get really the flat R4, and the minimal one, which is a degenerate. So the cone is not going to be 4-dimensional anymore, but it is collapsing full blown to a half line. So it's collapsing to a 1-dimensional guy, which is a half line. And if you stare at this is a description of the asymptotic cones of the universal cover of the counterexamples. If you stare at the universal covers of the manifold itself, then you're gonna get an even more non-trivial behavior, because in the family, if you stare at the family of the asymptotic cones of these guys, you're gonna see cones over quotients of the free sphere with respect to a discrete action, a subaction of the up action, and in particular, you're gonna get cones over length spaces. The possible choices of the length spaces really depend on the choices that you make through the inductive construction. But still, you can get this non-trivial behavior, and also, of course, also for the family of asymptotic cones of the manifold itself, you get radii shrinking from the maximal one to the lowest possible one, for which you get a half line also at the level of the manifold itself. So let me make the next, in the last few minutes, what I would like to discuss is some of the steps of the geometric construction. Let me make first a very broad comment about gluing. So the manifold, the universal cover is going to be constructed through an iterative gluing procedure. Let me make the comment, maybe possibly well known to most of you, that gluing with positive Ricci curvature is a tricky task. And this I would like to illustrate by the following remark to the effect that there are exotic spheres that can be obtained through the gluing constructions. So by gluing two copies of an n-dimensional disk along the boundary with the gluing non-trivial gluing diffeomorphism, this copies of the disk, of course, admit metrics with positive Ricci curvature, but a result due to Itchin back in 1974 tells you that you can find exotic spheres obtained through this construction that do not admit a metric with positive scalar curvature, and for theory, they do not admit any metric with positive Ricci curvature. So this is meant to illustrate that gluing, in general, gluing with positive Ricci curvature is a tricky task. However, for linear constructions dealing with gluing under the constraint that the Ricci curvature is positive or non-negative, let me mention a few works that, without the aim of being complete, that are at least morally relevant for the construction that we're going to discuss in the next few minutes. So first, Shen Yang in 1990 built metrics with positive Ricci curvature with gluing techniques on connected sums of several copies of product of spheres with dimensions greater or equal than 2. A related example is the construction due to rate a few years later of a matrix with positive Ricci curvature on any exotic 7 sphere. And but let me also mention these are still related to the at least morally related to the construction that we are going to go through later. Work of Perelman in 1994, work of Mendui dealing with the gluing and positive Ricci curvature under the assumption under an additional non-collapsing assumption. Okay, very well. Now let me address very briefly the geometry of one of the steps of the one of the geometric steps of the construction. So, and I would like to address the gluing step that we briefly addressed earlier, where we chose the non-trivial gluing diffeomorphism in order to glue the new copies onto the ends of the old guys. So what you should keep in mind is that the gluing, in order to make it geometric, is not going to happen straight away, but it's as in many gluing constructions, is going to happen through a gluing neck. And this picture is meant to illustrate very roughly the structure of this gluing neck. So the horizontal layers are meant to be the evolution of the six-dimensional component that is going to need to change while we move from the bottom to the upper part of the slide. The bottom is going to meant to display the picture at the scale approximately equal to little r subscript j-1, and the upper end is meant to display a picture of what's going on at a scale approximately equal to little rj. What you should keep in mind is that what must happen through this gluing neck is that an isometric action which is rotating on both the free sphere components at the bottom should be rotating on just one component at the end of the neck. So this is what our next steps are going to address. And I'm going to address this with a couple of intermediate steps. First, I'm going to discuss what's going on, forgetting about the equivariance, forgetting about the fact that we need to endow these guys with an isometric action. And then I'm going to discuss what happens at the level of the isometric action. So the first key statement, and Vitaly's comment was most probably alluding to that, is that if you stare at the diffeomorphism group of the product of two free spheres, then the key remark, which is what make on one end this construction possible and on the other end this construction non-trivial, is that this diffeomorphism group is not path connected. This is a statement due to Craig back in 79. And the first step that I would like to address for the construction is the non-equivariant one. So the statement of this technical lemma is the following. Imagine that you start from the standard product metric of two round metrics on the product of two free spheres, and you give me any diffeomorphism in the diffeomorphism group of this smooth six-dimensional manifold. Then the statement says that you can find a smooth family of Riemannian metrics that I'm going to denote by little g, little t on the product of the two free spheres with the following two properties. So you would like the Ricci curvature to be strictly positive for any time slice. So the Ricci curvature to be strictly positive for each of these metrics. And moreover, you would like the n metric to be isometric to the original one, but through an isometry, which is actually you would like the n metric to be the pullback of the standard round metric through the given diffeomorphism that we were starting with. Any comments? Okay, so let me make the obvious remark that if phi were to be isotopic to the identity, then the construction would be completely trivial, because you could take as a family of metrics GT, you could just fix a family of interpolating diffeomorphism. So you could fix an isotopy, let me call it phi t, and you could take, in order for the statement to be satisfied, you could just take a family of isometric metrics, where the metric at time t is just given by the pullback of the round metric at the initial time through the diffeomorphism phi t. So the construction would be trivial for diffeomorphisms that are isotopic to the identity. The non-triviality comes from the statement that we were mentioning at the top of the slide about the not path connectedness of the diffeomorphism group of S3 cross S3. Let me next address what happens at the level of at the equivariant level. So at the equivariant level, the key tool in order to build the gluing neck is the following equivariant version of the statement that we discussed a minute ago. So same setting, we start from the standard round metric on the product of two free spheres, and now we fix any integer which should play the role of the k appearing in the op 1k actions that we were discussing a few minutes ago. Then the statement says that you can find a diffeomorphism from S3 cross S3 to S3 cross S3 And you can still find a smooth family of Riemannian metrics, GT, on this 6-dimensional Riemannian manifold with the following properties. So still, you would like the time slices to be positively Ricci curved for any time. Moreover, now you make the further requirement that you want the construction to be equivariant. You want it to be equivariant with respect to the S1 1K op function. So you would like that the 1K op rotational action is isometric for any time slice. And moreover, you would like that the n metric is the pullback of the round standard metric that you start from with respect to a diffeomorphism. And this diffeomorphism is the kind of diffeomorphism that we need in order to make the gluing construct, the topological gluing construction work. So you would like that this diffeomorphism, such that the n metric is the pullback of the standard round metric with this diffeomorphism, is also conjugating the 1K action to the 1,0 action. So it's conjugating an isometric action, rotating on both components, and at a very higher, much higher speed on the second component, to a op function which is not rotating anymore on the second S3 component. Let me make, to conclude, to end this part, let me make the comment that it is maybe instructive and useful to, and much more elementary, I would say, to do an analogous construction for a family of flat Riemannian metrics on a two torus. So you would like to build, this is elementary, but still it is very much instructive. You would like to build a family of flat Riemannian metrics, so they are going to be all flat on the two torus, such that all the other requirements are met with the obvious changes. So I don't have time to discuss to give you more details about the some of the other steps of the geometric construction. Let me use the last couple of minutes to mention a few of the open questions that I find relevant in this area. So besides the obvious one about the validity of Milnor's conjecture in the remaining dimensions, so remember our discussion, Milnor's conjecture is known to be true in dimension 2 and 3, and it's now known to be false in dimension 7 and higher, of course, and there is the obvious question of the validity of Milnor conjecture in dimension 4, 5, and 6. And besides this obvious question, a couple of questions that I find very interesting are questions about the validity of Milnor's conjecture if you make further assumption on the structure of the manifold used there. And in particular, I believe that the question of Milnor, if you make the further assumption that the manifold is Ricci flat, is still open. And I believe it's the same in the case if you make the assumption, in the case where you make the assumption that the manifolds are non-negatively Ricci curved and Kähler. Another assumption, another question which remains open, given the structure of our counterexample, is the validity of Milnor's conjecture if you make the assumption that the universal cover has Euclidean volume growth. So this is a much weaker assumption than making the assumption that the manifold has Euclidean volume growth. Remember that under this assumption, Lee and Anderson proved that the fundamental group must be finite, but the question is still widely open in the case where you make the assumption, when you make the assumption that the universal cover has Euclidean volume growth, which of course is a weaker assumption. And the last assumption that I would like to mention is a characterization question about the possible fundamental groups that must arise for open manifolds with non-negative Ricci curvature. So remember, if you go back to the discussion about Wilkins' theorem, building on the earlier work of Way, that would have given a almost complete characterization of possible fundamental groups of manifolds with non-negative Ricci under the assumption that Milnor's conjecture was true. So it gives a characterization for finely generated subgroups of the fundamental groups. But now that we know that this is not the case, an interesting question is to completely characterize possible fundamental groups of manifolds with non-negative Ricci curvature. And that's all I wanted to say. So I thank you for the attention.
Thank you very much for your beautiful talk. Are there any questions?
I have several.
Please.
To your last point, can your construction be used to produce nilpotent but non-abelian examples?
That would be very nice, but we have no idea.
Okay.
Like, it would be very nice. It would be the
right.
It seems much more delicate. At least morally.
Well, I wasn't sure, right? So you thought about this, of course, right? Yeah. Also, can you say a bit more? I don't know, although this may be long, but even assuming that you can construct your matrix GT as you explained on S3 crosses S3, you actually need to produce not families of metric, but matrix of positive curvature on products and eventually on this big manifold. So you have to glue something. How does this come about? I mean, and what are the metrics on your nodes, right? You have this S3 cross D4s, right? And then I mean, what do you do with this?
So I can briefly discuss what happens in the step where you try to pass from the family of metrics with positive Ricci curvature to a metric with non-negative Ricci curvature on the cylinder, let's say. And this step is addressed through the following with an equivariant version of the following lemma due to Colding and Naber. This is the lemma that they use in order to show that many families of manifolds with the positive Ricci curvature can arise as asymptotic cones of manifolds with non-negative Ricci and Euclidean volume growth. So very roughly speaking, the abstract lemma tells you the following: once you are given a smoothly changing family of manifolds with non-negative Ricci curvature, you can scale them to have the same total volume. Once you are in the position in the setup where they have the same total volume, you can use an old construction due to Moser and conjugate them with the diffeomorphism in order to make the further restriction that they have constant volume form. Once you are in the setting where you have a family of smooth Riemannian metrics which are smoothly changing with respect to the time parameters, let's say, and they have uniformly positive Ricci curvature and constant volume form, then you can make basically a generalized work product construction to build a metric with non-negative Ricci curvature on the cylinder, let's say. And this you should view as a rough approximation of the cone metric, which is the metric that you would take in the case where the metric is really constant with respect to t. And there, the takeaway from this lemma is that if you make the metric change very slowly, then you can allow for changes in the coordinate expression of the metric. That's how we handle we pass from the family of smooth metrics with positive Ricci to the metric on the neck. And of course, there are several more steps.
You need to do this equivariant, right?
Yeah, and the other point with respect to their construction is that we need our construction to be equivariant, but this basically follows from the way. So the construction is explicit; it's not abstract, and you can check that the construction is really equivariant. And of course, there are then you need to make and all the other pieces with the metric, but those I would say so. Some of them are in the spirit of the gluing constructions of Shai and Yang, and some of them are morally in the spirit of the gluing construction of Mengui. I would say they are different, but they are morally similar. I would say that the newest step is this one, where we build the neck, which is conjugating the actions at the bottom and at the top part.
Thank you.
Hi, Daniele, can you hear me?
Yeah.
So I have a question, a basic question. So if I'm not mistaken, then this gives you like counterexamples for any dimension bigger than 7, right? Because you take manifolds and take product with Rn, or right?
Yeah, that's true.
Do you know what is the expectation in dimensions 4, 5, and 6?
The fair answer is that I have no idea. In particular, in dimension 4 and 5, and in dimension 6, there might still be room for building a counterexample with similar techniques, but so far we are not able to do so.
I see.
On the other hand, if one is willing to build either to prove that it is true in dimension 4 and 5, I feel that one really needs to come up with new ideas. And even if one is willing to build counterexamples in dimension 4 and 5, one really needs to change our answers is not gonna work, at least in a straightforward way.
I see.
Yeah.
Thank you.
You're welcome.
Is there any other question?
Yeah, I have another question. So you really depend heavily on the result of the diffeomorphism group of S3 times S3 not being connected, right?
At least morally. at least morally.
Yeah, I mean, the question is if, for example, you could do the same construction by taking different Hopf vibrations.
What do you mean? I'm not sure I got your.
So I mean, you can have actions of S1 on higher dimensional spheres, right? And be it like also that are analogous to the Hopf vibration in S3. I mean, now they're of course be different, but the question is if you can try to do the same construction instead of taking S3 times D4, taking higher.
It seems I don't see any obstructions, but the construction, on the other hand, the construction is really specific of the example that you are staring at. Like I'm not aware of any general tool for building such a family of metrics, and the way it works in our construction is really, really specific of the example you are staring at. So in principle, I would say that there are, so in general, so I think that there are cases where obstructions are known, like cases where you go back to something similar to the itching result that I was mentioning before. But in general, I'm not aware of any general obstructions, nor of any general construction.
Okay, thanks.
You're welcome.
Last question. Okay, if there are no more questions, let's thank Daniele. Thank you very much for your talk.
Thank you.